Okay, let's look into the question number 2. Okay, so what is being asked that biological oxygen demand of water sample can be determined by the following series of reactions. So they have given us the reactions, 3 reactions. The final step of titration of the sample with sodium thiosulfate, that is Na2S2O3. Okay, a student analyzed 300 centimeter cube of samples of water taken from the school pond, one immediately, that is at day 0, and the other leaving it sealed in a dark cupboard for 5 days, day 5. The following results were obtained for the titration. And the question is being asked, A1, determine the mole ratio of S2O3, that is the thiosulfate ions, to oxygen O2 using the balance equations. So let's begin our story. So let me write it down. The first equation, that is 2Mn2 plus oxygen 4OH minus, 4OH minus plus, what I have done, let me rewrite it. 4OH minus, that is the basic solution, giving us 2MnO2 plus twice H2O. This is the first reaction. Then let's look into the second one. So manganese dioxide, MnO2, which has been liberated from the first, is getting titrated against iodide ions in the acidic medium, 4H plus, giving us Mn2 plus I2 plus 2H2O. Okay, so let's first balance this. There are 2 MnO2 and here, so let me put the new this one. So it is very clear so that it becomes simple. 2 MnO2. Let me remove this, make it 4 because I'm multiplying by 2. H plus gets doubled. So, okay. So this becomes 8H plus 2 MnO2. Okay, sorry. This is 2I2 and this is 4H2O. And then the last step, twice S2O3 2 minus plus I2, but now since it's a 2I2, so let's make it double in this last step itself. Okay, let me put 4 S2O3 twice I2, giving us 4I minus plus twice S4 A2 minus. Okay, and now they're asking us to compare S2O3. So in this case, S2O3 are 4 moles as compared to oxygen, which is a 1 mole. So it's a straightforward, the ratio is 4 moles of thiosulfate ions versus 1 mole of oxygen. That's all. So you should be careful in balancing this, balance the necessary kind of this one which are getting reacted. Okay, so that was a trick, simple. Okay, so MnO2 twice MnO2, that's why this becomes twice I2, and then this becomes twice I2, so this becomes 4. Okay, simple. Hope this is quite clear, very simple. Okay, continuing with the question number 1A, 2A2, calculate the number of moles of oxygen in the day zero sample. So first of all, just a quick understanding of these three reactions. So what is our purpose? So understand what is our purpose. Purpose is to find out the oxygen, okay, in that given water sample. So what we do, we basically, okay, allow that for the incubation of for 5 days, okay, so that whatever is the organic material which is there, that will get decomposed, and then we try to estimate how much was the oxygen which has been consumed, okay, by that whatever that organic material, and that is called a biological oxygen demand, because that affects basically the aquatic life. Okay, very simple. So in this case, what we follow is a very simple. So our purpose is to estimate this, okay, oxygen. But the problem is that it is not really straightforward. So what we do first, okay, we carry out, okay, the reaction, okay, with Mn2 plus ions of oxygen in basic medium, OH minus. So it will get this Mn2 plus will get oxidized to MnO2. Then what happens that again MnO2 cannot be estimated directly. So we react MnO2 with iodide ions. Okay. So MnO2 now gets reduced back to Mn, okay, Mn2 2 plus, and iodide ions have been converted into iodine. Now what is the advantage? That iodide ions are colorless, I minus are colorless, while I2, we know iodine, it is having a distinct violet color, dark violet color. So this, whatever is the iodine which is liberated, okay, in the second step will be again titrated with thiosulfate ions, okay, and we get back I minus, that is iodide ions which are colorless, okay, and we get S4O. So this is called a back titration. So by knowing basically this part S2O3 volume, we can calculate the original oxygen. Okay, that is the trick. That's why this is called as back titration. Okay, back titration. That means we go to the last step and estimate what is there in the first step. Okay, so now let's understand that we have been asked to calculate on the day zero sample. That means this is the sample which is for S2O3 2 minus salts. Okay, so what is the volume? Now let's understand that first. What we need to estimate is its moles of S2O3 2 minus in day zero sample. So how to calculate? Simple. Moles are equal to molarity or concentration multiplied by volume in dm cube. So what is the concentration? The concentration is this, that is 0.0100 moles per dm cube. What is the volume? Volume is 25.8, but just be careful, it is a centimeter cube, so don't forget to divide by 1000 to convert into dm cube. Okay, it's quite straightforward. Okay, so whatever are these are the number of moles. Okay, so these are number of moles So calculation 2.58 into 10 raised to minus 4 moles. So please remember this is S2O3, thiosulfate. But our interest is moles of oxygen. That means in the first step. Just now we calculated that the ratio between, okay, so let me repeat, S2O3 2 minus 4 moles versus oxygen 1 mole. It means that this is the ratio. So if we have to calculate moles of oxygen in day 0 sample, it is going to be equal to 2.58 into 10 raised to minus 4 divided by 4 moles. Okay, so it could be 6.45 into 10 raised to minus 5 moles. Simple. Okay, so the real important part to learn in back titration, okay, we calculate the first step, whatever the reactant concentration or moles, using the last step, okay, last step titrant. And why we do that? Because it is not easy to estimate directly. So we try to find out which are the known kind of reactions, and based on that we use the simple stoichiometry, like what should be the ratio, and based on that we estimate. Okay, so this was a good quality question on the back titration. Continuing with the question number 2A3. Okay, day 5 sample contained 5.03 into 10 raised to minus 5 moles of oxygen. Determine the 5-day biological oxygen demand, okay, of the pond in milligram per dm cube or parts per million. Okay, so let's quickly understand, or just to recap, what do you mean by BOD? That is the biological oxygen demand. So BOD 5, that means for the day 5. So what you do, you take oxygen in day 0 minus oxygen in day 5. Okay, so this is how we will calculate, okay, what is the oxygen, because this is what, see what is going to happen, that in day 0 we'll be getting the original oxygen. After that, whatever is the organic contents in that water, they will start getting decomposed using the bacteria microbiological activity, and that microbiological activity will start consuming the oxygen, and because of that, by in day 5, okay, the oxygen will get reduced. So whatever is the difference, okay, from day 0 to day 5 sample, that is nothing but a biological oxygen demand, okay, BOD 5. So just now we calculated oxygen, okay, in day 0, that is 6.45, okay, into 10 raised to minus 5 moles. In day 5, it is given as 5.03 into 10 raised to minus 5 moles. So what is the difference? Difference is equal to, subtract, so 1.42 into 10 raised to minus 5 moles. Okay, so this is basically the BOD 5, but it is in terms of the moles. And again, It is basically, but in what sample? Okay, so please remember that, so for concentration, okay, is equal to moles upon volume. So that is 1.43 into 10 raised to minus 5. These are the moles, and it should be in the dm cube. Please remember that in this question it is given as 300 centimeter cube. So 300 divided by 1000, this will give us dm cube. Okay, so quickly let me take out my calci and check up. So what will be the answer? 1.4, sorry, 1.42 into 3. So that will give me 4 point. Okay, so it should be, just a minute, 1.42 it is equal to, so it should be giving us 4.73, okay, into 10 raised to minus 5 moles per dm cube. Okay, now what we will do, we will calculate. So this is the concentration, or what we called a molarity. Now we'll calculate the, basically in terms of the gram. So okay, so mass of oxygen per dm cube, that is going to be equal to 4.73 into 10 raised to minus 5 multiplied by 32.0 gram per mole. Okay, and this is moles dm cube. Okay, so how much we will get? Let's do the quick calculations again. 32 multiplied by 4.73. So that will give us roughly around 137.6, okay, into 10 raised to minus 5 gram per dm cube. Okay, sorry, I made a mistake in calculations. So this should be 151.36, okay, into 10 raised to minus 5 grams per dm cube. Okay, now what we do, okay, it is simple, that basically we need to calculate in terms of milligram per dm cube. So what we are going to do for milligram, first we will convert into multiply. Okay, so we are going to multiply this with 10 raised to 3. So 151.36 into 10 raised to minus 5 multiplied by 10 raised to 3. So gram to milligram per dm cube. Okay, So this is going to be either in ppm, okay, or in milligram per dm cube. This is the answer. Straightforward. So it was a good conceptual question, calculation intensive. Okay, continuing with this question number 2B1, calculate the percentage uncertainty of the day 5 titer. That means this is the reading, okay, day 5. So they are asking us what will be the percentage uncertainty. So if you observe very carefully, they have given us this uncertainty. That means for every kind of a titer, this one reading, we are going to get plus or minus 0.1 centimeter cube. This is the uncertainty for every reading. So how to calculate percentage uncertainty? So you take whatever is the uncertainty which is given, divided by the actual reading, 20.1, multiply by 100. Okay, so let's do this. So 0.1, so let me, sorry, 0.1 multiplied by 100 divided by 20.1. So the answer is 0.50. Okay, so this is the percentage uncertainty. Extremely simple. So uncertainty in the reading divided by the actual reading multiplied by 100. Okay, extremely simple. Okay, question number 2B2. Suggest a modification to the procedure that would make the results more reliable. Simple. We have seen that there is some random error, okay, whenever we have been indicated like this, plus or minus 0.1 centimeter cube. This is called random uncertainty. What do you mean by random uncertainty? It means that there is some kind of uncontrollable or unavoidable sources of error, okay, which are resulting into this kind of uncertainty. It could be limitation of that given instrument, maybe a least count, or there can be another sources of errors which cannot be eliminated completely. So how to minimize this? So in case of random uncertainty, the best way is to go for several readings. Okay, that means you repeat the experiment number of times and take average of those. Take average of these readings. So in case of random uncertainty, it is the best way is to go for a repeat the experiment several times, take the average of those readings, and that will be more or less more precise, okay, more kind of a realistic number. Okay. So that is the best bet. Hope this is quite simple.